Inside an extra high voltage substation, the power grid operates at an extreme potential of 765,000 volts. For the grid to operate without collapsing, control centers require highly precise, real-time measurements of this voltage to trigger protection relays and monitor power consumption. At lower distribution voltages, engineers measure power using a standard inductive potential transformer, which steps down the voltage using magnetic coils wrapped around an iron core. But scaling that magnetic induction principle up to 765 kV physically breaks down. A standard iron core designed for that much potential would have to be massive. The volume of copper and the amount of insulation required to prevent a catastrophic arc flash make a pure magnetic step-down economically and structurally unviable. This photograph shows the industry-standard hardware used to solve that exact problem, the Capacitor Voltage Transformer, or CVT. Its entire purpose is to take the 765,000 volts from the overhead transmission lines and safely step it down to a standard 110-volt output that sensitive metering equipment can read. Achieving a step-down ratio of nearly 7,000 to 1 without destroying the equipment requires abandoning pure magnetic induction. Instead, the CVT relies on a two-stage internal architecture. The first stage happens entirely within the tall, towering section that connects directly to the power line. This upper section is known as the capacitive voltage divider. Looking at the engineering schematic for a 765 kV unit, we see how it reduces the incoming voltage. The column is housed inside a weatherproof outer shell made of heavy-duty porcelain. The actual active components doing the work are stacked tightly inside. These are individual capacitor units wired together in one continuous vertical series connection. Electrically, this long stack is split into two distinct groups, a primary capacitance section called C1 and a secondary capacitance section called C2. When alternating current passes through a capacitor, it encounters impedance. By placing two capacitor groups in series, they act as a pure voltage divider. The raw 765 kV grid power enters the top of the C1 stack. Because voltage drops proportionately across capacitors in series, a much smaller intermediate voltage is tapped exactly between the C1 and C2 groups. To handle the electrical stress without shorting, these capacitor elements are made of alternating paper and polypropylene foil, tightly wound and bathed in synthetic dielectric oil, to yield a total capacitance of 8,800 picofarads. This stack survives the raw grid by distributing the electrical stress along its height, but the intermediate voltage pulled from the tap point is still around 10 to 20 kilovolts, too high to feed directly into a modern protection relay. That intermediate 20 kilovolts travels down the column and enters the solid metal tank at the base of the tower. This base is called the Electromagnetic Unit, or EMU. Returning to the schematic of the base tank, we see a shift in technology. Housed at the bottom is a medium voltage transformer. Because the voltage is already reduced by the tower, a smaller, safely insulated magnetic transformer performs the final step down to the required 110-volt output. However, routing current through the upper capacitor stacks introduces an electrical side effect. The capacitors force the AC signal's phase angle out of alignment. Protection relays calculate impedance based on strict phase timing. This phase shift introduces blind spots where grid operators cannot accurately detect a fault. To correct this, engineers install a specific compensator next to the transformer, the series reactor. In AC circuits, inductance acts in direct opposition to capacitance. The reactor provides the exact amount of inductance needed to cancel out the capacitive phase shift, pulling the signal back into resonance. Combining capacitive division with inductive compensation allows the CVT to output a perfectly timed replica of the grid, maintaining a strict 0.2 class metering accuracy. Beyond electrical accuracy, these units must survive outdoors in highly exposed substations, where temperatures can swing from freezing winters to blistering summers. The entire hollow cavity of the CVT is filled with synthetic dielectric oil to insulate the components. When ambient temperatures rise, that liquid oil expands. When they drop, the oil contracts. If you completely seal a rigid, fluid-filled chamber and heat it, the thermal expansion creates internal pressure, which would eventually fracture the porcelain tower. To prevent bursting, the design incorporates an expansion system at the top, a stainless steel bellows. As heated oil increases in volume, it pushes against the bellows. The metal accordion compresses inward, giving the oil room to expand and keeping internal pressure constant. This flexible mechanical seal prevents the oil from ever coming into contact with atmospheric moisture, which would ruin its dielectric strength. By acting as mechanical lungs, the bellows allow the entire internal system to remain hermetically sealed and maintenance-free for decades. Even with strict environmental sealing and phase correction, there is one condition that threatens to compromise the CVT: sudden grid faults. When line switching or short circuits occur, they can trigger an electrical phenomenon called ferroresonance, a sustained high-frequency oscillation of voltage. This is a volatile feedback loop triggered by the interaction between the capacitance inside the CVT tower and the nonlinear magnetic inductance of the grid during a transient event. To protect the internal components from the thermal and electrical stress of these oscillations, engineers include a final component in the bottom tank, a damping circuit. Wired across the secondary terminals, this circuit is designed to instantly absorb and dissipate the rogue oscillatory energy before it can damage the transformer windings. This document is a factory ferroresonance test report for a GE 765 kV unit, demonstrating exactly how fast this damping circuit reacts. Look at the top oscillogram. The technicians intentionally subjected the CVT to a short circuit at 80% of its rated voltage. You can see the sudden spike of unstable energy. The table on the right proves the damping circuit engaged immediately. The RT, or recovery time, shows the system tilled the ferroresonance and stabilized the wave in 162 milliseconds. By coordinating capacitive division, inductive compensation, and active damping, the CVT maintains measurement integrity even under volatile grid conditions. This specialized architecture is what allows 765 kV measurements to be both safe and precise, turning raw transmission potential into manageable, readable data for grid operators.